So, yeah, a year or two ago, we developed this class through a lot of requests coming in from customers. So it was originally designed to be obviously about a 3-day hands-on course. We're going to cover section 1, which is just basic fundamentals. We're going to have a couple of short videos to show during this class that I felt like that were evident or fell right in line with the purpose of this class. So with that note, let me just kind of state the purpose. I work with a lot of lease fleet companies, end users, et cetera, and over the course of several years, we've seen a large influx of new blood into our industry. And sometimes these guys are great mechanics, but the organization which they work with don't necessarily have individual electrical people that do just electrical. And so what we're seeing more and more now is a mechanic, a person that's very mechanical, is having to do a lot of electrical work too. So we wanted a way to try to give them some basic understanding of electrical practices and adapt them into the ability ultimately at the end of this course to have them have a better understanding of how to look at, read, and decipher schematics. So I chose the course when we developed this to start with the very, very most basic things. So with that, I'll get started. And as David noted, please, if you have any questions, this section is not very long. We do have time, so pop in and ask a question, and I'll do my best to answer, right or wrong. Also, on a special note, before we do get started, this is an instructor version of the course curriculum that we put together. There are some mistakes. I know about most of them, but I'm always kind of finding new ones, and I just have not had time in the last couple of years to edit and update that. So if you see something, and I'll try to catch them as we go along and point out the mistakes that are printed in this course throughout the rest of our couple hours together. So fundamentals of electricity, we want to cover this as just a real basic quick thing. So a lot of people think of a loop of wire as a conductor, but or a loop of a wire that is a conductor as a circuit, but that's not necessarily true. To make a full circuit, we also need to apply electrical pressure or voltage, and we're going to use this term several times throughout our time together today. And when we say voltage, I like to think of voltage as pressure for other examples, but a lot of times in formulas, when we're working out formulas, voltage is indicated by the letter E, and E stands for electromotive force, and it dates way back into the early 1800s, late 1700s, that terminology. So electrical pressure causes current. Current is indicated by the letter I. And this, again, is for formulas that we work out later today. I stands for impedance. It can also relate to amperage, and I think most of us have probably heard that term. The current is opposed by resistance, indicated by the letter R. And this is the only letter that really makes good sense in mathematical formulas, R for resistance. I like that one. And the physical pathway for the current to flow is called an electrical circuit. So again, if we were kind of recap over to the far right-hand side of the page, voltage, E, electrical pressure that moves electrons, current, I, which is impedance, electrical current flows as a result of pressure applied, so think of that as amperage again, and then resistance. So this could be a coil in a relay, an actual physical resistor, an incandescent light, an LED light that we see in a control panel. So all circuits are going to consist of specially designed resistive components. Some of these components are called resistors. The omega sign is used to indicate resistance value in ohms. So one term that I get a few students that'll pop up in their head, they'll call me up at night after a class and needing a little troubleshooting, and they'll use the term ohmage. There's no such word as ohmage. Please don't use it. It's resistance, but it's measured in units of ohms. So I think we've covered most of this on the first page, but we'll just recap real quick. So voltage is an electrical force. So think of it as electromotive force or pressure, which causes current to flow through an electrical conductor. Anything that can conduct electricity, most metals. Measured in units of volts. Symbol for calculations is E. Now, disclaimer right here. In some cases, more modern terms, because in a lot of people's thinking the E doesn't make sense, we are starting to see substitutes of V for voltage in some of the equations. So, and we'll probably see some of that through the day or in next week's class. Current. Current is the flow of electrons through a conductor measured in units of amps, amperes or amps. Symbol of A for most current day-to-day use practices. Symbol for calculations is I, which again stands for impedance. Resistance is the opposite offered to the flow of an electrical current by a substance through which it is passing. Measured in units of ohms, symbol for calculations is R. Let me pause for just a second. I want to recap something. Okay, so in some cases, I want to kind of stem in on something else too. This is my disclaimer for the day. A lot of people these days, when I was growing up in the 70s, you know, everybody would say, oh, you know, electricity flows from the positive to the negative side of a charge. And in more recent years, we hear in the scientific world that actually electrons, they say, oh no, actually the electrons flow from the negative side to a positive side. And if you're into watching a lot of educational stuff on TV or something, documentaries, et cetera, you'll even maybe have stumbled across some things where people actually discovered that, scientists discovered that lightning seems to really come up from the ground to the clouds, not from the clouds to the ground. I don't know. I'm not a scientist, but for our purpose through this whole section of electrical stuff, we don't care what the electrons do. We're really caring what our voltage does. And for simple terms and for schematic interpretation, we're not looking at it in a scientific way. We're looking at it a more practical way. So for the rest of this course, we're going to be thinking, hey, our voltage flows from positive to negative. So that's kind of my disclaimer, but I like to stay because there's always somebody will pop up and say, well, wait a minute. All right, so inside an electrical schematic, there's going to be lots of symbols. We're going to cover some general symbols. The symbol to our right in figure 1-2 is just a generic battery symbol. Some cases, if somebody has a 24-volt battery system, we're going to see a total of 24 lines. 12-volt, we might see only 12 lines. That's not always the case. It depends on the draftsman, the engineer who's doing the schematic, but there's always notations in at least electronic schematics that will signify, hey, you might see an icon that looks like this, indicating a battery or battery supply. No matter how many lines are in it, we're going to have a notation in it that tells us what we're intending the voltage to be. Most of the things we run up through in our industry are 24 volt. The symbol to indicate a resistance can be seen in figure 1-3. There's several different variances of this, but this is one of the more common ones. The resistance of the main conductor wire will be considered in all circuit designs, but will not be considered here in our class. So if we think about a wiring harness on an industrial engine today, we may have 100 foot of wire in a circuit. There's going to be some resistance in that wire. Sure, any engineer that's designing a system has to take those type of resistances into allowance. For our exercises throughout this course, we're going to assume that there's no resistance in wires and we're only looking at the resistance that we place in the circuit. So please make note of that as well. Figure 1.4 displays a common ground symbol. I have seen all three of these types used. The first one, where it's just three lines crossing, is the most common. It's the most common that I use in drawings that I do and most that I come across, but the other two are perfectly acceptable. So just kind of know what those are. So one of the points that this page is making is we can draw a schematic out in a couple of different ways, and I'll give you two examples down here at the bottom. I have a 24-volt DC battery in figure 1-5 or 1-5A, I'm sorry, and I have a battery at the top, and I have it noted it's 24-volt DC, and I have marked the positive side and the negative side, and I have a resistance in it. It doesn't matter what the value is, this is for this example, but our flow is from the positive through the resistor and back to the negative. Likewise, in figure 1-5B, same thing. It's the same circuit. I have the negative side of my battery shown going to a common ground or a ground block. I have the positive side going through the resistor and to the same ground or a common ground block. And so this could be an engine block, a compressor package skid, et cetera, but it still does the same thing. The voltage is going to do its best to go from the positive through the resistor into ground, return through a ground connection into the negative side of the battery. Any questions so far? Great. So measurement devices. Be wary of measurement devices. Not all are created the same. So a voltmeter. A voltmeter is used to measure voltage or voltage potential. Do we have voltage there? Always place across the device, never place in series with the circuit. Units, volts, or millivolts, small m with a big V behind it. So if we look at figure 1-6, we can see that we have our battery. From the positive, we flow through our resistance and back into ground. So let's just say this is a 9-volt battery as a good example that everybody can kind of envision in our head, and this is nothing more than a light bulb that we've wired up to the battery. That's the light bulb is our resistor. So if we were going to measure voltage, we would just measure on either side of the light bulb. So an amp meter. An amp meter is used to measure current flow. We always place it in series with the device, never place across the device. Units of measure is amps and or milliamps. So same circuit, but now what we've had to do, we've had to break the circuit and we've inserted our amp meter to where our flow from the positive through the amp meter to ultimately power our light, our resistor in this case, and then back to ground. And if anybody's ever done this with a meter, they know that they have to move the leads on the meter. We'll cover that a little bit later. An ohm meter is used to measure resistance. Always place across the device. The device should be disconnected to isolate it from parallel loads. So if I have a complicated circuit board or a complicated wiring harness or wiring circuit in a control panel on a unit out in the field, if I'm wanting to measure the resistance of it, I can't just start measuring resistance. I have to isolate what I'm measuring resistance on. So I may have to go undo connections at the far end of the skid or at the other end of the panel, but it has to be isolated or you're going to get a false reading. If you don't isolate it, you're wasting your time. Never test while power is on the circuit. The ohm meter supplies its own power. So this is what we do. This is where we stop when we're doing these classes in person. I might have 10, 12 people attending a class, and everybody will have a meter. And so what we do is we do a buddy up or a team system to where we actually start measuring the voltage with 1 meter of their neighbor's ohm meter. And that's a lot of fun because we actually find out that every meter is different depending on the model and the manufacturer of it. So I'm not going to go through this in too much detail, but current modern day meters, one of the most common brands out there that I see people using are Fluke. There's several different models, from a cheap budget inexpensive model to a more complex model. But they've all got symbols on them, and not necessarily everybody knows what those symbols are. So I gave a good example down here. The one I like to start with is DC voltage, which is just a V with a straight line across the top. In most cases, sometimes it does have a dotted line. AC voltage, in this case, they have a millivolt symbol here, but it's indicated by a straight line with a ripple above the V. Ohms, or a way to measure resistance with the units of ohms. Continuity, diode test. Prods, that's when we get into capacitors and whatnot, so I'm going to kind of skip over that one. In fact, a lot of the meters I've seen don't even have that symbol on them in some cases. DC current, so it would be the same DC symbol, 2 straight lines, but with a A under it instead of a V. So that's just something that you can kind of reference from. And any of this information, of course, is always available online. If you do have a Fluke meter that you use, you can always reference the Fluke website. They have some really good interactive training purposes, training aids on their website, I've discovered. Any questions so far? Great. So we've talked about a voltmeter, an ohm meter, and an amp meter, but a lot of times what we do is we use meters that are actually called multimeters, volt ohm meter. In the old days, I still have one floating around somewhere, is a meter like you see in figure 1.9. It's actually an old analog meter, and it had an analog gauge on it. Very difficult to read, very accurate, just as accurate as a modern day meter, or could be, depended upon the quality of the meter, of course, but very, very hard to read. Because you had to know what unit you were in, what scale range you were in, and then how to interpret. And if you're like me, I need a magnifying glass and some 4-power reading glasses to see anything these days. One key note about an old analog meter: they do one thing that a current digital meter does not do. They do generally apply a slight load to the circuit, which can be good in some cases. They had their purpose, and for that reason, some people do retain these things if they still have a working one. Most modern day is a digital volt ohm meter. There's multiple brands out there. You don't have to go out and buy a Fluke if you don't have one. But that said, I would also steer you clear of going to the Dollar General store or Harbor Freight Tools and buying the $5 digital volt ohm meter and trying to use it. If you have a faulty meter or an unreliable meter, you should just throw it away and go get you a good one, because if you're getting false readings on the system that you're trying to troubleshoot, it's going to catastrophically cause you to go down the wrong rabbit hole. Just last week, I carry 2 different Fluke meters with me, but my primary Fluke meter, I'm not sure of the model right off the top of my head, but I was doing a test in my lab, and I noted that I was getting some readings that I shouldn't have gotten. And after a little bit of testing, I realized that my 2 leads that plug into these terminals right here were faulty. And got to thinking about it. those particular meter lead probes that I was using were about 4 to 5 years old. Immediately, once I figured out that they were bad, I threw them in the trash, got on Amazon, ordered another pair, about $20 to $30. So a common term for this you'll hear some people say is just a DVOM, which stands for digital volt ohm meter. One unique thing about this meter, because it's digital, it produces no load when you're measuring voltage on a circuit. And that can snake bite you from time to time. And so I tell you what I'm going to do. I'm going to stop sharing the screen for just a moment. And I'm going to switch over, and I'd like to play a video. Dave, if you're listening, what I'd like you to do is once this video starts playing, just give me a sound check. You can text me on my cell phone. That would be great. I want to make sure everybody can hear this.
Will do.
Hey guys, this is John Nance with Altronic. A lot of people have been asking what is the difference between true voltage with amperage power behind it and what we call voltage potential. This day and time with a lot of solid state electronics, it really can whoop a lot of people when they're out in the field trying to troubleshoot. So I'm going to do a best example to show you what voltage potential is, and then I'm going to make a second video that shows you kind of different ways of checking for voltage potential versus true voltage. So what I've got here is a classic excerpt from one of our panel designs where we have 103 switched fused battery power, so there's 24 volts on it, and we're bringing it into a relay, and this is just our symbol for a relay in most schematics. And this voltage, 24 volts DC, is present at all times. It also enters into a flyback diode for a remote relay to be added on this circuit if somebody wanted that option. And in this case, they would use it to shut power off to an engine control system. On this relay PR2, they're using this wire DE5 from the A2 terminal to turn the relay on and off with a digital output 5 from a DE4000 terminal module. Now, what this does is when this digital output 5 turns on, it closes internal contacts and connects it to ground, and we can have a lot of different control strategies that would do this, but then it would complete a ground path for the PR2 relay, and the PR2 relay would energize and turn on. Now I'm going to show you a different example of this section of the schematic in another schematic, and let's use it to show exactly what voltage potential is. This is from a slightly different design, from a 3000 design. The relay was renamed PR1 for it, but the same principle applies. We have wire 103 that comes through a check valve diode. So that means voltage can only move in this direction, and it enters in and it comes into the coil of the relay. Now that coil has a lot of resistance to it. It also enters into a light emitting diode through a 3.92K ohm resistor and makes it back to the DE5 wire. And then finally, there's a flyback diode only allowing excess voltage from an inductive load that occurs, or self-inductance, when the magnetic field in this coil for the relay collapses, to where if there's a voltage surge on the ground line, it can be dissipated back into the system and loop around in this path and slowly diffuse. So if DE5, now this DE5 wire comes from the A2 terminal, again, it's tied to all these things you see here, and it goes back into digital output 5 on either the DE3000 board or the DE4000 board, as I showed in that previous example. Now, all of this up here has to do with what the switch contacts of the relay are doing. So this is irrelevant. Don't even think about this for right now. But remember, voltage is just like pressure. So if I measure voltage between a ground point in the panel and any of these points along here in the schematic, I'm going to have 24 volts. But if I don't have this circuit grounded and I measure this DE5 connection back at the digital output 5 and I hadn't switched on the ground, I'm likely to see 24 volts with a digital volt ohm meter. And that is because with a not a completed circuit, the resistance factor that's taking place in here and right here is irrelevant until I complete the path of the circuit. So as soon as I ground this circuit, the voltage will dissipate and drop to 0, or should, provided my ground path is sufficient enough to handle the voltage that remains after the resistance. That's a short, quick example of voltage potential. Again, with the ground path not completed, I'll see voltage, the same voltage here as I do here. With the ground path completed, the voltage on this side, because the resistance will drop. Think of it as a water hose. If I plug one end of the water hose, but then pressure it up, but then shut the supply pressure up, there's still pressure on that hose. But as soon as I opened the discharge into that hose, the pressure escapes out immediately, and then there's no more pressure. So think of the voltage in that manner. Thank you for your time. If you have any questions, please email me at jon.nance, N-A-N-C-E, at herbiger.com, H-O-E-R-B-I-G-E-R. And look for the next video because I'm going to show an example of how to test for true voltage versus voltage potential. Thank you and have a great day. Okay, so I hope I didn't confuse you too much by showing you that video, but I'm going to show you the second part of this video. And if you found yourself getting lost on this part, this next video is going to really kind of tie things together. And at the end of it, if you still find yourself getting lost, don't worry. Things as we go through this course of the next few weeks will explain a little bit more, and I'll probably imagine myself playing these two videos another time, either next week or further down as we go through this series of this basic electrical class. So with that, I'm going to start the next video.
Hello everyone, this is John Nance with Altronic. Some of you may have watched a video that I posted called What is Voltage Potential? And in that video I said I would make another one and show you what, give you an explanation of what, how to test for voltage potential. So I'm going to do the best as I can on this. So what we're wired up to right now is a training demo for a DE3000. And we can see that the DE3000 is a manual stop. None of my outputs, my digital outputs, or at least digital output 5 is not turned on right now. So it matches the schematic that I used in my demonstration. Digital output 5 is used to turn on a relay in this design and for powering accessories. So all digital output 5 does is turn on ground, but because it's coming from the relay that I showed in the first video, if we measure the voltage on it, we should see 24 volts. So what I've done, because I don't have so many hands, is I've permanently attached my ground probe for my voltmeter into a ACOM grounding block down here where my pressure transducers wire in. And so I'm going to come in and I'm going to measure the voltage at digital output 5, and we're going to see that we have 24.09 volts. Now, just for fun, I'm going to move down here to the power supply where circuit 103 is coming in, and I'm going to do the same thing, and you can see that I have the same amount of voltage. Now, here's the fun part. So, a lot of you guys have heard that, don't use test lights, but this is where I like to use test lights. I got this one at Lowe's. It's a 24 volt, or I think it can go from 12 to 24 volts DC. It's a simple test light. It has like a little LED in it rather than an incandescent bulb, but it is enough to put a load onto a circuit. Versus a digital volt ohm meter, remember, does not put a load on a circuit. So let's test this test light. I have the other end of it grounded right now to case ground on this demo. And if I touch it to the 103, we can see that it lights up. But if I move it up here where we saw voltage at digital output 5, you can see that it doesn't light up. And that's because the voltage that we saw there was just voltage potential. Likewise, if we measure the voltage at the same time at digital output 5, and we see we have 24.9 volts, come on in with that. And if we touch the test light to it, no light from the test light, and we can see that we have a little bit of voltage there, but 1.29, and that's just because the resistance of the test light. And again, remember, the test light is not lit up. That red light you see is coming from that red light in the background. So that's a good example of testing for voltage potential. I'll show you one other thing that's going on here. Another thing, because this test light creates a ground path, here's my PR1 relay that digital output 5 lights up or powers up. So when I touch this test light to digital output 5, you'll notice, and you might be able to hear it. I'll get the camera as close as I can to it. So that is the difference between voltage potential. Now what's happening is there's 24 volts coming to the A1 side of this relay, and that voltage has no path to go to, but it's trying to ground at digital output 5. And when we ground digital output 5, it completes a circuit for the ground path for that relay, and that's why we're seeing that relay energize. But because of the resistance in this relay, we don't see any voltage, or we see very little once we've grounded it. With no ground path, that voltage comes all the way through, but it's voltage potential, not true voltage. In some cases, what we've had is we've had some lightning storms recently, and we've seen some damage to some of the diodes that are in the circuit for this relay, short closed, and that will apply a full 24 volts true voltage to digital output 5, and it'll burn this board. And one way to test it is with a test light. If you have true voltage, that test light will light up just like it does when I touch it to circuit 103. Now let's see how the circuit's supposed to work. If I energize that circuit, I can push reset, and it should enter in a power mode. Now the digital output 5 is turned on. PR1 is on. We'll come up again and measure the voltage with a voltmeter, and because it's a true path to ground, we see 0.007 volts. So the ground is going through the board on the DE3000 terminal board. And that, my friends, is one of the best ways I can describe how to test voltage potential. I hope you enjoyed the video. Hope it teaches you a few things. If you have any questions, please email me at
Okay. Any questions on that? Okay, so we should be back to my regular presentation right now. Dave, can you just give me a sound check, being that I've been switching some things back around?
Yeah, it sounds great, John.
Okay, thanks. So the significance of that video and my purpose of showing you so quick early on into this section, voltage potential, is because I would say over my whole career, 30 some odd years, when doing electrical work, that's my number one thing that sends me down the wrong rabbit hole, where I'm off replacing the wrong part or misdiagnosing the system and the difference could be having a unit down for 3 days versus 3 minutes, and literally that quick. So that's a huge thing, understanding voltage potential and understanding the circuits that you're working on and having the abilities to expect, well, I know I'm going to see a little bit of voltage there because of this or that. But another good check is to definitely add that to your arsenal if you don't already have one. Little low voltage test light. They say if you get the ones with the LEDs in them that you don't necessarily damage electronic circuits like you would if you were using an old-fashioned one with an incandescent light bulb in it. I'm not an expert in that matter, but that's what I've been told. So any questions before I go to the next page? Okay, so moving on, the purpose of this is to learn a little bit about Ohm's law, learn about how to do circuit evaluation and calculations. And again, ultimately at the end of this, we're going to, hopefully have a better understanding of how to read a schematic, decipher a schematic, and troubleshoot a system using the schematic. But in order to do all that, we need to cover some really neat basics. So I've inserted a graph up here at the top. It's not the greatest in the world. I'm going to try to explain it the best I can. If you're measuring resistance with your multimeter, your digital volt ohm meter, sometimes you might see, as an example, 4.0 ohms. Now, if there's not a letter symbol behind it, that's 4 ohms. A common thing in our everyday life that we come in contact with that might have 4 ohms is a stereo speaker in a car, as an example. And sometimes audio fidelity people will refer to that as impedance, but how much resistance it has. If you see a letter value behind that same number, 4.0K, then that means 1,000. So for doing mathematical formulas in what we're going to cover later in the section for Ohm's law, we have to convert that. We can't say 4.0K. In our math formulas, we have to spell it out. So if you have a K, K means 1,000. And what you do is you would move a decimal places 3 spots to the right. So if you had a reading of 1.045 K ohms, that would equal to 1,045 ohms. Likewise, if you have a large capital M behind your value that you're seeing on the meter, that is mega ohms or million. So you would move your decimal place 6 places to the right. So as an example, 0.654 mega ohms would spell out, if you had to write it out for a math formula, 654,000 ohms. So you can kind of see where we're going with this. One of the last ones would be a small m, and here's one of our first mistakes in today's lesson. That should be a lowercase m, not a capital, for milli. So milli would be 3 paces to the left. Now, I think I got a good example of milliohms on the next page. Well, millivolts, same thing. Now, here's milliamps right down here at the bottom. So 1.76 milliamp, we would move the decimal place the opposite direction, so it becomes 0.00176 amps is how we would call that out. So a good example is, more than likely, anybody on this call has heard of the term 4 to 20 milliamps. So if we wanted to write that out for a math formula, it would be 0.004 amps. If we wanted to use 20 milliamps as our example, we would write that out as 0.020 amps. Are there any questions about how this conversion works? This is kind of a worksheet that I do with my students, and when we do this class face-to-face, they fill in the red. In this case, we're looking at the instructor version. I pray and hope that most of these answers that I put in here are right. Any questions from anybody at all? Okay, because this is important to understand. So here's a little exercise that you can do if you find yourself with nothing to do and you want to kind of go back from this class and visit. You can use software on your computer right now to do a screenshot of this, or you can just use your phone to take a photograph of this. But if we want to test or check our voltmeter, we can connect the red test lead to the volt-ohm input connector and the black lead to the common input connector. Now, I'm going to back up a page or two just in case you're not sure what I'm talking about. So when we look at this modern day digital volt-ohm meter, here's your main voltage and resistance input checkpoint right here, red. And here's your common. And then you have two others down here on this far end that are marked in amps. This one has an A over it for amperage, and this one has a MA, a small m and A on it for milliamps. And we can't see in this figure, but if you grab your meter that you use on a daily basis and start looking, it'll tell you what the fuse rating is. So keep in mind, there is an internal fuse that travels between this connection and this common connection, and this main amperage connection and this common connection. All meters are a little different. All meters have a different rating fuse on them. Most meters, when people come to my classes, we find out have a blown fuse in them, and we'll cover that as we go through the course of why. So if you connect the red test lead to the main volt-ohm input and the black test lead to the common, turn on the function switch to DC voltage position, and just note what your meter reads, just with the leads not touching anything. And the reason this is a good exercise, it's kind of like a good way to fact check and test your meter. You remember a little while ago I told you I just discovered last week that I had bad leads, test leads on my meter. Well, this is how I verified that. So another thing you can do is you can turn the function switch to the ohm position, and with the two test leads separated, not touching each other, the display should read OL, which stands for overload. And if you touch the two test leads together, the display should read 0. But most people will find, and here's a really good point, most people will find that when they touch the two test leads together on their meter that they do not get a 0 reading. And the reason being is because the meter has a little bit of resistance built into it already. So do the probes, your meter leads. They have a little bit of resistance built into them. So again, this is a great way to test your meter before you start on anything to make sure your meter is up in good working order. And if you've got friends and everybody has a different brand meter, you'll be really shocked to see the different readings that you get from one model or one brand of meter. And this is where I'll always generally have a student that might have a dime store meter that they brought in, and usually we prove that they got what they paid for. If they got a $20 meter, well, they got a $20 meter. So the meter is, when we're doing electrical work, the meter is our number one go-to tool. So invest the money and have a good one. Last test is to touch the red test lead to the amp connection test port on the meter and write down your reading. So if I back up a step, sorry, I'm having to look at one page at a time. So we have the function meter in the ohm position. So what we're doing when we do this last test is we're checking the resistance to see if we have a good fuse in our meter. And this is where we find that a lot of the guys, when they come to classes, that they have actually blown fuses in their meters. Any questions at all? Okay. So DC voltage measurement. If we connect the red lead to the volt ohm input connection and the black lead to the common input connector, we set the function switch to DC volt position, and then we connect the red test lead across the component being tested. So again, here's our battery source. It could be a 9-volt battery for simplicity's sakes, and maybe we have a little light right here for our resistor. So we're going to touch the red one right here on this side. Then we're going to turn on, and we're going to touch the black one right here to this side, on the negative side. And we're going to turn on the circuit being tested and observe the reading. The instrument's polarity sensitive will indicate polarity too. So again, if I hook the red probe of the meter to this side, the positive side source, and I put the black here, what I should see is just voltage. If I reverse and push the black on this side and the red on this side, I may see a negative, or should see a negative side in front of my value, indicating that I have it reverse polarity on my test. Now, if all I'm doing is looking for voltage, it doesn't really matter. But if I'm wanting to know, if I'm on an unknown circuit and I want to know where's my positive source coming from, where's my negative source coming from, that's a useful little handy fun-filled fact and tool built into our meters. So on a DC current, we connect the red test lead on the meter to the A input, which stands for amperage. We connect the black lead to the common so it doesn't move. And don't forget to check and make sure that what is your fuse, kind of have an idea what you should see for amperage on your circuit, and check and make sure that your meter's rated for high enough amp flow through it for testing so you don't blow up your meter. Most meters have a 10 amp rating, but some are less. And then like that example I showed a few moments ago, that particular meter had amperage port for larger flow rates, as well as it had a milliamperage for smaller flow rates. Set the function switch to DC amp position, turn on the power to the circuit device being tested, open the circuit and insert the meter in series with the device being measured. So what we do is we actually break the circuit and we connect our red test probe to the battery supply and run it through our meter, and then out the black test probe from our meter back into the circuit to complete the circuit. So we're actually completing the circuit with our meter inserted in there so we can get an amperage reading. Any questions on how to test for amperage on a circuit? Okay, one thing I'll note is I've been saying that a lot of people have blown fuses when they come to my classes. What they'll do is they'll put a meter in this setup to measure amperage, but when they finish that test and they go back to maybe they're measuring resistance or maybe they're probably measuring voltage, I'll back up a page. So they go and start using their meter like this again, but they forget to swap that lead from the amp input. They forget to swap that red lead on their meter from the amp input back to the voltage and resistance port, and that's when they always blow their fuses inside the meter. And usually those meters have a little specialty fuse that's sometimes hard to find. So try not to do that, and/or try to always carry spare fuses with your meter. And don't ever put a fuse in larger than what your meter is rated for. Resistance measurement. So we want to connect the red test lead to the volt-ohm input connection on the meter and the black to the common. So notice the common scenario, the black meter is always on the common on any of these tests. Set the function switch to the ohm position. If the resistance being tested is in a circuit, turn off the power. Not only did you turn off the power, isolate that resistance. So if I have a resistor installed in a circuit and a wire going from each end and landing somewhere else, I have to isolate those ends, or my test for that circuit that I'm trying to measure the resistance on is null and void, because there's too many other things that can throw it off and cause me to get a false reading. Connect the test leads to the circuit. When measuring high resistance, be careful not to contact adjacent points even if they are insulated. Also, keep your hands off the test lead conductor so that your body resistance is not registered. So here's another little fun test. If you're just playing with your meter on your bench and getting familiar with it, put it in the resistance check by turning it to the ohm symbol, and with your left hand and your right hand, hold each one of your probes where your thumb, between your thumb and your forefinger, and you'll actually be surprised. You'll get all kinds of readings. Very, very neat. It's no different than what an EKG machine does and a lot of the fancy stuff medical equipment does at the doctor's office. Read resistance on the display. If a high resistance is shunted by a large value capacitor, allow the reading to stabilize. So some circuits may have capacitors in them. Watch out for those anyway, because they can zap you if they discharge, especially on ignition systems. But also understand that those capacitors can throw some readings off. So don't just take a quick reading and back off from anything. I always recommend when you're taking a voltage reading, resistance reading, or anything, to put the meter there and watch it for at least 30 to 45 seconds. Make sure it's stable and not changing and shifting on you. So continuity check. Now, if I'm just troubleshooting an electrical circuit that's supposed to turn something on or off, continuity check and the voltage check is probably my two favorites. I don't get in much to actually measuring resistance, and I hear guys out in the field always measuring resistance. What I like about the continuity check is it just is a quick check. If I'm in a quiet area where I can hear, or sometimes you'll see me out in the field. If it's a noisy location, I'll take my meter and I'll hold it like an old telephone between my shoulder and my ear, and when you touch the two probes together, you'll hear your meter buzz, and it just gives you a nice buzz. There is a little bit of voltage produced by the meter coming from the red probe, and when it returns to the black probe is what triggers the buzz. A little bit more so source voltage than the resistance test. So be leery of what circuits you're doing. Again, I generally only do this on circuits that are designed to turn things on and off. Never put your meter in a resistance test or a continuity test and go to an instrument such as a pyrometer or a channel on a DE3000 or 4000 that is designed and or dip switches set up currently to read thermocouples, because you will damage the circuit on the board. The red test lead is connected to the volt-ohm input connector. The black lead is connected to the common input with both test leads separated on the display. Your display should register OL for overload, or out of limits is the correct term, not overload. Now place the rest test lead to one end of the cable and the black lead to the other end. When continuity is established, an ohm symbol will appear. Sometimes it will show you a value. I'm adding that on the display. but more importantly, a test tone. So depending on the type of circuit, I will use this very, very common, just a really quick rundown, trying to figure out, maybe I'm trying to just do a pin out on a harness to figure out which wire's which. Any questions on that? Okay. So here's kind of a little worksheet. The questions are answered in red. I'll run through it real quick. When using a volt ohm meter to test a circuit, the instrument is never placed in series with a circuit. That is correct. When performing a voltage or current measurement, the red lead is placed where in respect to the circuit? It's on the side closest to the positive source. When performing resistance measurement, what precaution is to be observed in regards to the meter's safety? The circuit should not have power applied, because you don't want to damage your meter. What does OL indicate when performing measurement? Out of limit, not over limit. So there's another misprint in our wonderful document today. 5. Is it normal for the last digit to the right sometimes to flicker on a digital volt ohm meter? So we hadn't covered that, but yes. And the reason being, if I'm going out 3 decimal places, so let's say I'm doing 12.001 volts. Sure, there's a little bit of variance, sometimes on all electrical circuits. And that's a good sign that you see that value changing maybe or flickering a little bit, because it means that the meter is actually working and collecting its samples properly. While measuring a positive 24 volts, the meter displays a negative 24 volts. Why? We covered that one. The polarity is reversed or the meter's hooked up backwards. So again, your positive probe of your meter is expecting to see a positive voltage signal, and the black probe if your meter is expecting to see a negative voltage signal. So that is a good point. By going through this, not only could your meter maybe be backwards, but if your meter's right, then maybe somebody hooked up the batteries wrong. I've seen that happen a few times. When testing continuity, the tone works up to a resistance value of, now we hadn't covered this one, so this is a good thing. So the tone works up to 50 to 100 ohms, so it varies from 1 meter to the next. So again, if I'm just trying to figure out a pin out between one end of a harness to the other end of a harness, the continuity test is good because I'm not expecting to see 50 ohms, more than likely much less than 4 ohms on just a wire, whether it's 5 foot long or 50 feet long. Any questions before we advance to the next part? Okay. So this is something that's a little outdated, but I did want to include it in. It falls into play with some of the exercises, hands-on exercises that we do when we get into the circuit section, which won't be till next week. Still trying to figure out how to do that one online, so y'all bear with me next week if you tune in. But most common days nowadays, digital electronics, technology has gotten really good. Resistors have gone from little round guys with a wire out at each end, like you see in the picture up here, to a little small square chip that's soldered onto a PCB or a printed circuit board. Some cases too, for doing troubleshooting work or field work, we still may get a resistor if it looks like this, but no longer do they really have bands on them anymore these days. Usually they have like a silk screened image that just shows the value on them, which is actually kind of nice. But in the old days, yeah, we had to learn and understand these color codes. So I'm not going to spend a lot of time on it. I just wanted to cover it and show it to you. You can get this information anywhere, online, Google, if you ever need to. I grew up in the time where we would ride our bicycles down to Radio Shack and buy resistors and take them home and build stuff, and usually figure out a way how to blow up 9-volt batteries was our goal. But if you ever do run across resistors and you see these colored stripes on them, understand that they do mean certain things, and you can get these charts to decipher those things. But most days what you'll see is you'll see a silk screened image that shows the value and the tolerance. Now the tolerance is a pretty important thing. I believe it is the smaller the number. I may be wrong on this, but the smaller the tolerance, the more accurate the resistor is. Anybody that knows different, please chime in and correct me on that one. So this is more verbiage of what I was just babbling about. So we're just going to skip this page. Now, every resistor does have a watt rating. The most common little cheap resistors, if you do find a Radio Shack's opened, or if you're online and you order like a little home project electrical scientific test kit, maybe like to work with one of your kids at the house for their science fair project or something, they're going to be little small quarter watt and they're going to have a very bad tolerance, but they'll let you build a lot of stuff with them. We'll use stuff in our panels, I believe up to 3 watts is sometimes common, but the wattage has to do with how much heat we have to expect and how much heat that resistor can tolerate and or dissipate. So just be aware, and you generally the higher the wattage the resistor, the larger the resistor is. In fact, if we print this document out, this was actually pretty much an accurate representation once it was printed out on paper. So now we want to get into circuits. So if I totally confused you earlier when I showed those 2 videos, hopefully we're going to start breaking some of that down a little bit. So the word circuit comes from the Latin word circum, which means to go around. Webster defines a circuit as a path or line of electrical current. We kind of covered that definition on the very first page today, so I won't spend too much on that. A completed pathway for a circuit will exist whenever 2 unequal charges are connected by a conductor. But also remember, we have to have voltage, pressure, amperage, and generally a resistance to complete the circuit, unless we want to blow a battery up. Completing an electric circuit pathway consists not only of the conductors, but includes the voltage path through the system. So I liked this example, and that's why I chose to put it in here. I've got my high potential, positive charge. I've got my metal wire doing its best to try to flow everything over to the negative side. This is good old school stuff. For the class in the power supply, voltage flows from the high potential to the low potential. And this is the disclaimer that I also said, because there's always somebody say, well, wait a minute, my science teacher told me electrons flow the other way. Yeah, okay, but not for what we're doing. All right, so here's another thing that I like to make sure everybody understands. So I like to refer to an electrical circuit as a water hose. So just imagine on the side of your house, you've got a 100-foot water hose, would round it up, 100 foot long. Think of voltage as an electrical force or pressure which causes current to flow through an electrical conductor. As an example, we can think of water pressure in a garden hose. So, and again, I said this kind of earlier, I think in that video, if I go to the side of my house and I turn on the valve on the side of my house, water starts flowing through that hose. I've got pressure at one end. By the time I get 100 feet away, I may not have that much pressure, right? But if I plug that hose 100 feet away at that end, the pressure builds and it equalizes. Again, if I go back to the house and now I shut the valve, I still have pressure trapped in that hose, but if I open the far end of it, 100 feet down the rope, that pressure escapes and drops to nothing instantly. Think of that as voltage. Current is the flow of electrons through a conductor. As an example, we can think of an amount of water, flow, or volume through a garden hose. So if I've got this hose flowing 100 foot long, I've got my valve wide open, it's wide open at both ends. If I'm flowing 10 gallons per minute into that water hose from the side of the house, I've got 10 gallons per minute coming out of the far end, correct? You usually get somebody that challenges me on this one, but I am right. So if somebody said, oh no, you would only be getting 5 amps out. Well, if I'm flowing 5 gallons per minute in, I got to be getting 5 gallons per minute out. Either that or that hose is expanding. Or maybe in the case of a capacitor, maybe I'm charging a capacitor, I guess you could say. Hopefully that helps kind of explain things. Now we throw in resistance. The resistance is the opposition offered to the flow of electrons current by a substance through which it's passing. As an example, we can think of a restriction in the garden hose, like a kink. So if I'm sitting there flowing 10 gallons in the hose per minute and 10 gallons out of the hose per minute, but all of a sudden my kid comes around and kinks the hose, well, maybe I'm getting a little bit of flow out the far end of that water hose, but not that much. Maybe he reduces me from 10 gallons per minute down to a half a gallon per minute. Well, likewise, on the opposite side, close to the house, if I reduce the output from 10 gallons a minute to a half gallon per minute, my input into that hose has been reduced from 10 gallons a minute to a half gallon per minute. The only difference is between the kink and the house, I have higher pressure. Between the kink and the discharge side of that hose, I have very low pressure. Same thing as electrical electrical resistance. Any questions at all on this part? Because if you understand this, you understand electricity. Okay. So everything we just covered is kind of necessary to understand before we get into Ohm's law. By knowing okay, so I'll go through a little thing. So Ohm's law is, there's a picture of Mr. Ohm. He doesn't look too happy. I'm not sure what years that he walked this earth, 19th century. So what, 1800s? Does that sound about right? So remember we talked about voltage, symbol is E, amperage symbol is I, resistance symbol is R. So if we work this Ohm law formula, if we know 2 of any given value, we can always calculate the other one. So it's a little bit of an algebra if you catch my drift. So I'll just read this. By knowing any of these 2, voltages, amps, or ohms, it's possible to determine the third value. This is done mathematically by the use of Ohm's law formula. Early in the 19th century, George Simon Ohm proved that a very special, precise relationship exists between voltage, amps, and resistance. This relationship is called Ohm's law. He discovered it. He gets to name it. Ohm's law states the current in a circuit is directly proportional to the applied voltage and inversely proportional to the circuit resistance. The basic equation for Ohm's law can be expressed as the current is equal to voltage divided by resistance. So here's how I memorize it. E over I equals R. If I can remember E over I equals R, then I can draw this out. And from this one drawing, following what I learned in algebra, I can write these 3 different equations down. Any questions on this part? And y'all are great. Okay. So obviously we're not going to build any circuits today, but we will kind of go through 1 or 2. So figure 119 demonstrates that with 1 volt applied to a circuit with 1 ohm resistance, that 1 amp will flow. So if I've got 1 volt and I've got 1 amp and I've got 1 ohm, if I go back and work Ohm's law out in any shape, way, or form, my answer is always 1, right? So what I'm going to do is I'm going to give you a little bit of an example, something common that we do. And I'm going to stop sharing this. And do my best to try to draw something for you. Okay. So one of the common circuits, very common circuits is, and I made mention of this, is a 4 to 20 milliamp circuit. So we throw this term around loosely all the time. If we're writing it out, we may write it out like this. Four to 20 milliamps. Now, one of the most common places we'll use this is like a pressure transducer, a 4 to 20 milliamp pressure transducer, and this is a lot of fun. So now that we know Ohm's law, and we know how to convert 4 milliamps to write it out as amperage, we can say 0.004, pardon me, I'm not that good at writing stuff with a mouse, times one of the common resistance values we use in a lot of the Ultronic products are 200 ohm resistors. So I can write the value of 200 for my resistance, and I'll go on and draw an R over that, and an I over that. So 0.004 times 200. If any of you guys are working it out, I hope you are. That's a decimal place, or decimal point. Should be 0.8 volts. So there's our E. This is something that I use almost weekly, if not daily, since working for Ultronic. So likewise, if we do the same formula, but now we draw out 0.020 amps, so there's our I, times the same resistance value, because it's not going to change, equals, no decimal place, 4 volts. Did anybody work that out with their calculators while I was drawing it out? So you may be thinking right now, what good does this do me? Well, if you use any 4 to 20 milliamp pressure transducers and you're using it, say, with the DE3000 or even the new DE4000, you know that, wait, we wire those things up different and we flip the dip switches different. So inside those terminal boards, which is one of the reasons why we flip the dip switches, we short out our signal side coming in from the pressure transducer to ground through a 200 ohm resistor. So what we do is we convert a 4 milliamp signal to voltage, and the voltage reading is 0.8. So at 4 milliamps, we should be seeing 0.8 volts. Likewise, if we're at full range on that pressure transducer and we're getting 20 milliamps, we're doing the same conversion, and the answer is 4 milliamps. So if I have a pressure transducer that's 0 to 100 psi and it's a 4 to 20 milliamp pressure transducer, my voltage range is 0.8 to 4 volts. So 0 pressure equals 0.8 volts. 100 psi would equal 4 volts. Another common place we do this is with speed control on governors. We put out a 4 to 20 milliamp signal, except we substitute the 200 ohm resistor with a 250 ohm resistor. And if we do the same math formula, 4 milliamps times 250 is going to equal 1 volt. And 20 milliamps times 250 is going to equal 5 volts. So we can drive a 1 to 5 volt signal with a 4 to 20 milliamp signal source. So actually, I ran through this a little bit quicker than I thought. I know we have a little bit over 30 minutes left, but this concludes section 1. Next section is series circuits. So I'd like to open the floor up for questions, answers. There may be some things that we touched on that somebody's got a few questions about, or maybe something I didn't touch on that somebody's got a question about. I'd love to answer questions.
As usual, John, it's an excellent review. I guess as John said, we'll just open it up to the floor for any questions that you might have for John. Again, you can just
John,
space bar. Please go ahead.
John, I got a question for you on some of those drawings, schematics that were in there. Under
Yes, sir.
R for resistance, there was also a letter L, a smaller L. What does that represent?
Let's take a look at that. So you're talking about the presentation I've been showing?
Correct.
All right, let me see if I can find that. I think those were some of the colored schematics that were in the very early part of the, yeah.
I mean, I'm trying to get the symbology down, and
Sure.
that gets through a curve.
Okay, so you're going to hear Nance confession time at the moment. I have no earthly idea, to be honest with you. When I put this course together, I did a lot of the drawings in the course curriculum on my own, but to save time, some of the stuff is just images I found online on the internet.
Okay.
To me, the L doesn't mean anything, man. But
Okay.
now that you pointed it out, if I ever go back and update this thing to fix the mistakes that I've known and that I've had in it, maybe I ought to use a little whiteout tool and get rid of that L. But that's a good catch, actually.
Well, John, I'm sorry to put you on the spot there. Sorry about that.
No, don't be. That's a good one, because I guarantee you, if you ask that question, there were at least 5 others thinking it.
Hi, John. Hey, this is Matt Donham here with Ultronic. I just wanted to let you know L typically means inductance on a series circuit or inductive type circuit with current flow. So I can't see the slide that he's referring to, the gentleman's referring to. So, but L typically means inductance. So you could have current through an inductive or resistive type load.
Tell you what, Matt, I've got it back up on the screen right now. Can you see it now?
Okay. Well, that's not that's a resistive load, but that L is not representative of a inductor.
Okay. Well, you know what? You actually just solved the rest of the recipe and saved me from having to edit this for future classes with whiteout, because I'll just call it a resistive load. How's that?
Well, that's what it is. Just like you said, it's a light bulb. It's some type of load.
All right. We're going to refer to that from this point on as a resistive load.
Thank you, gentlemen. I appreciate it.
No, that was a fun one.
just trying to help. Thank you.
I appreciate it, Matt.
Thank you, Matt.